Welcome to AP Physics Made Easy. My name is Eric Sampson, and what I want to do is get you a 5 on your AP test. So I suggest we get busy learning ourselves in physics. Now, today's episode deals with the independence of horizontal and vertical motion. It's a topic that is very much not intuitive, and it is covered quite a bit on the AP test. So let's get on it, all right? So on the AP Physics test, you'll often be asked to solve what are called ballistic motion problems, in which you have an object that's traveling through the air in a parabolic path. Now, most of these problems involve one of two scenarios. So one scenario that comes up a lot is an object that is projected horizontally off a table surface. So it's moving horizontally across a table or off a cliff, and then it falls through the air. The other type we get is one in which we have an object that's projected upwards from the ground at an angle, all right, where you angle theta, and it travels up through the air and usually comes back down to the same height it was launched from. It doesn't have to, but that's usually the scenarios that they're going to give us. So the key to solving these problems, and you need to wrap your head around this as soon as you can, you have to keep in mind the independence of the horizontal component of motion and the vertical component of motion. They don't influence each other. They are independent of each other. So like here, what I see is this one here is traveling at a constant speed vh, right? But if I notice, the vertical velocity gets smaller, goes to 0, and then turns negative. So the thing is, the vertical component is affected by gravitation. Usually these problems are given to us on Earth where g is -10, but they could be on another planet or the moon, okay? But the bottom line is the vertical motion only is subjected to acceleration g. Since there's no force acting horizontally, generally what we're going to do is ignore any kind of drag force or air friction. So in that case, there's no acceleration horizontally. So the object, that's why it just keeps traveling at the same speed the whole time, because there's nothing to make it go faster or slower in the horizontal direction. All right, so again, the key concepts are objects do not accelerate in the horizontal direction, but objects do accelerate in the vertical direction at g. Okay, so are you starting to get the message? All right, let's try this here. So let's just say I have an object. It is projected horizontally through the air at 10 meters per second. It has no vertical component of velocity. Well, let's check in on it 1 second later. What we're going to find is that it's still traveling at 10 meters per second horizontally, but whereas it had no velocity vertically initially, after 1 second, it's going to be moving downwards at 10 meters per second. And after 2 seconds, it's still traveling at the same speed horizontally. Why? Because there's no force causing it to change its motion, no acceleration in the horizontal direction. But there is gravitation causing it to accelerate at 10 meters per second squared in the downward direction. So now it's going 20. And I think you can see where we're going. A second later, it's traveling still at 10 horizontally, but it's going 30 vertically. All right, so let's play this little imagination game, okay? So imagine that I have a gravity switch. Always wanted to have one of these. And this guy just switched gravity off. So now there's no gravity, all right? And the person's going to throw a ball horizontally off a cliff at 20 meters per second. Well, if there's no gravitational force, then this ball is not going to accelerate vertically, all right? It's going to not move upwards or downwards. So what I find is 1 second later, it's still going 20 meters per second, and it's traveled a distance of 20 meters. And a second later, it's traveled another 20 meters. And a second later, it's traveled another 20 meters because it's going a constant 20 meters per second because there's nothing to make it go faster or slower in this horizontal direction. Now, because the horizontal is not subjected, and this is super important, there is only one kinematics equation that we can use when an object is not accelerating, and is this one here. And since things don't accelerate in these ballistic problems in the horizontal direction, this is the only equation you can use. So this equation is pretty easy to use, but let's just go ahead and work our way through it. So I'm going to start with the average velocity equation, which is the only one I can use for objects that are not accelerating. And I'm simply going to substitute in 20 meters per second for the velocity, and I'm going to substitute in 3 seconds for the time. And now I'm just going to solve this for the delta x value, and I'll get 60 meters. So in this time, it travels 60 meters horizontally. That's not particularly challenging, hopefully. Well, let's do this now. Let's go back to the gravity switch and turn it on. And this time, we're just going to take the ball and drop it. We're not going to throw it horizontally. So it has 0 horizontal motion, 0 vertical motion initially, And let's just see what happens as time goes by. Well, after 1 second, we'll find the ball is 5 meters below where it was initially. After 2 seconds, it's 20 meters below its initial position. And after 3 seconds, it's 45. Remember, it's accelerating, so it's going faster and faster each second, going further and further. Well, what equation would I use to solve for these distances? Hopefully you remember it's that super useful equation, d equals 1/2 at squared, which in this case we're just going to call it delta y because it's the change in the y position. And instead of 1/2 a, we'll be specific and say, well, it's 1/2 g because there's gravitational acceleration involved here. But this is the equation we have to use to solve for these positional values, these vertical positional values. So let's just go ahead and see how we would calculate using these equations. So I'm going to start off with this. And I'm going to substitute in and say, well, g is 10, the time was 3, and now 3 squared is 9, 9 times 10 divided by 2, it gives me 45 meters. That's how I arrived at that value there. Well, let's see what happens when we actually throw the ball. So I'm going to throw it horizontally off a cliff with gravity on, and it's traveling at constant speed horizontally, and that constant speed I believe is 20 meters per second. It has 0 initial velocity in the downward direction. So let's just see what would happen to it as it flew through the air. Well, it's going to take a parabolic path every time. So at time 0, it just leaves the person's hand. There it is. Now, after 1 second, it should have traveled 20 meters horizontally and fallen 5 meters. Because gravity makes it fall 5 every second using delta y equals 1/2 gt squared, and the horizontal velocity never changes. So the next second is going to travel another 20 meters horizontally, and in this case it's going to fall down to 20. And then the next second is going to travel another 20 meters horizontally, but it's going to travel all the way down to 45. And you'll notice it traces out this beautiful parabolic path. Now, here's something that our hearts tell us should be true, and it's just wrong, okay? And it is this. An object's horizontal velocity does not affect the amount of time the object is in the air. I mean, if you were to drop a rock from shoulder height, it'd be in the air maybe, I don't know, about 0.6 seconds. If you fired it through a bullet through a high-powered rifle level, it would be in the air the same amount of time. It's not going fast, doesn't keep you in the air. So horizontal velocity, all it does is it determines how far an object travels in the horizontal direction. But what determines how long it's in the air is the height. And if the height stays constant, well, then the time stays constant. Now, from before, we saw if it's 20 meters of fall, that takes 2 seconds. So the time is 2 seconds. If I project this with an initial horizontal velocity of 0, it's going to travel 0 meters in the 2 seconds it takes to fall 20 meters. But if I throw it faster, now I throw it instead at 10 meters per second horizontally. This vertical height is what's going to determine how long it's in the air. 20 meters, if I use that equation, that delta y equals 1/2 gt squared, I see it's 2 seconds. So this object is going to be falling for 2 seconds, but the whole time it's going to be traveling forward to the right at 10 meters per second. So therefore, it will travel a total distance of 20 meters horizontally. And similarly, if I throw it faster, now I throw it twice as fast. So if I throw it twice as fast, it's going to go twice as far because it's going to fall for the same amount of time. Now, if an object is going off a flat surface and I change the height, well, if I change the height, I'm going to change the time. Okay, so let's just say this one went off a 5 meter a 5 meter cliff at 20 meters per second. It would take 1 second to fall this far. And since it's traveling 20 meters per second horizontally, in the 1 second it takes to fall, it will travel 20 meters and it's here. But what if everything was the same except the cliff was higher now? Instead of 5 meters, it's 20 meters. Well, it takes 2 seconds to fall 20 meters. So this object has 2 seconds to travel at 20 meters per second horizontally, and it ends up going 40 meters. And if the table is even higher, now it's 45 meters. Well, if it's 45 meters high and I'm traveling 20 meters per second, I'm going to fall 3 seconds. And in those 3 seconds, I'm going to travel 20 meters each second, which makes me go 60 meters. All right, so the thing is, for height, I'm going to use this equation here to find the time. So basically, in these problems, the big trick is, remember, you're going to use the height to find the time using this equation, and you're going to rearrange that for time and get this every time. And you will see these a lot on the AP test. So be ready. Now, when you're solving problems with an object moving horizontally as it goes off an elevated surface, like a ball off a table, here's the approach you take. So you're going to use this equation here, the average velocity equation, to find the horizontal distance traveled here, okay? And you're going to use h equals 1/2 gt squared to find the amount of time it's in the air before it reaches the floor. All right, so let's just try this here. So I have a ball thrown horizontally off a 30-meter high cliff. It's traveling at 40 meters per second horizontally as it leaves the cliff. So how far away from the base of the cliff does the ball land? All right, so the thing is, this is what's going to decide how long it's in the air. So I know I'm going to use this equation here to find what I'm actually looking for, delta x. So I'm going to rearrange this for delta x, and so I see delta x is equal to the horizontal velocity times the time. Now the time I'm going to get from using this. So for the time, you use h equals 1/2 gt squared. Now I'm going to rearrange that for time, which gives me this. And now I can simply substitute this for this in the expression. So I have my initial equation for the position of it. I'm going to substitute in this value for the time, and I get this. Now I'm just going to basically substitute in the values I was given. So v was 40, h was 30, and what I end up getting is 98 meters is how far it's going to travel horizontally. Now, when a ball is thrown horizontally at velocity v off cliff of height h, it lands distance x away. You know, this is the kind of questions you mostly get on the AP test. They usually don't ask you to do calculations. They want you to use proportional reasoning. Then they say, well, where would it land if it was thrown at velocity 2v? Okay, well, what we need to do is we need to find the expression. Well, the expression we had was this, if you recall from before, from our last slide, we had this. We had x is equal to velocity times the square root of 2h over g. So from this, I can see that x is proportional to v. And so since x is proportional to v, if I double v, I'm going to double x, and there's my answer. But what if we did this instead? What if we said, well, the ball is thrown horizontal velocity v off cliff of height h. It lands distance delta x away from the cliff. What would happen if it was thrown from height 2h instead? So again, the trick is write the expression, which we have here, all right, from before. Now, in this case, I see how is x proportional to h? Well, it's proportional to the square root of h. So x is proportional to square root of h. And if you've forgotten how to do proportional reasoning, please go back and watch that video because it is such a big concept of Physics 1. And the thing is, it makes AP Physics 1 easy. Okay? Now, so if I put a 2 in front of the h, it's going to be square root 2h. So basically, I have a square root 2 in front of square root h, so I had to put a square root 2 in front of the x. Well, let's go ahead and try another one. In this case, instead of changing v or h, we're going to change g. We're going to say, where would it land if it was thrown on a planet with double the gravitational acceleration of Earth? Okay, so again, you start off with the expression that you derived, and then you say, well, x is proportional to 1 over square root g. Then, if I put a 2 in front of this, I have to put a 1 over square root 2 in front of the x. And now I have my new distance. Well, let's look at the other kind of problems we get. And the other kind of problems involve objects projected upwards at an angle from the surface. So look at this one here. If I want to find how far away an object lands when it's projected at an upward angle, the trick here is you've got to figure out the horizontal and vertical components. And in the next video I publish, it will be about how you do that. But for today, I'm just going to give you those values. So I'm just going to make a 3, 4, 5 triangle here. So in this case here, I'm going to use the vertical component to find the amount of time the object is in the air. And I'm going to use the horizontal component to figure out how far it travels horizontally. So whereas before I used delta y equals 1/2 gt squared for the time, I'm not going to be able to do that here because this has an initial velocity, and that equation I just mentioned doesn't work if there's an initial velocity. So how do we go about doing this? Let's start by how I find the time. Okay, so this doesn't help me. How fast you're going horizontally does not tell you how long something's in the air. The vertical values do. Either the vertical height, in this case the height is 0, or the vertical velocity, which is what we have here, which is 30 meters per second. So in this case here, I'm going to use this. I'm going to use the vertical component to find the time in the air. I'm going to use this equation here. A is equal to delta V over T, but I'm going to expand the delta V to be V final minus V initial, and here's why. I know what my initial velocity is. It's positive 30. So it's going to go upwards at positive 30, but when it comes back to the ground, it's going to have come down for the same amount of time it went up for, so it's going to be going negative 30. So let's substitute these values in. Here's my final value, here's my initial value. So I have negative 30 minus 30 over delta T equals negative 10 because gravitation is in the negative direction. And I find it's in the air for 6 seconds. Now that is how you're supposed to do this. Let me show you a shortcut that I personally always use. So if you have what I call up-down problems, like these things are going up and they're coming back down, there's this super easy trick. Basically, since the object, at least this works really easily on Earth, right? Since objects slow down at 10 meters per second squared, you just take this initial velocity and you divide it by 10, okay? And they say, well, that tells me how long it would go up for, but it's going to take just as much time to come back down, so all I have to do is just double it, right? So let's just try this here. So I threw it up at 30, so 30 divided by 10 is 3, and if I double that, I get 6 seconds, which is what we had before. So it's a really easy way of doing this, but you definitely have to, when you look at an up-down problem, you have to say, okay, I have to use the initial velocity and the acceleration equals delta V over T equation. So if I want to find out how far it travels horizontally, what I have to do is I have to take into account the horizontal velocity, and I'm going to use the vertical component to find the time in the air, which we just did. So remember, for horizontal motion, this is the only equation I can use. Why? Because it's not accelerating horizontally, and this is the only kinematic equation we can use when things are not accelerating. So let's just go ahead and substitute into here. I know that V is horizontal is 40, and we already found that the time in the air was going to be 6 seconds, so therefore this object is going to travel 240 meters. All right, so let's just reiterate this and wrap this up, shall we? Sorry, this is kind of a long one, but it's an important one. This definitely comes up a lot on the AP Physics test, and you really need to attend to this and make sure you have this solid in your mind, okay? So if I have a horizontal table or a cliff with an object going off it, I like to call these ball-off table problems, which you get so many of on the AP test. You're going to use this equation here to find how long it's in the air for. Then you're going to use this equation here to figure out how far it travels horizontally. For these up and down type problems, what you're going to do is you're going to find the vertical and horizontal components of velocity. Again, I'm going to teach you how to do that in my next video. So once I have the vertical component, I'm going to use this with a vertical velocity, and then I'm going to, or I could use the shortcut, right? So I can just say vertical velocity divided by 10 times 2. And then I'm just going to, once I find that time value, I'm going to substitute it into this equation here to find the horizontal value. So I know the horizontal velocity because we found it here, and now I know the time. As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that, or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.